So our next speaker is going to be Austin Williams from Oregon State University, part of the great lab down there with Brett Dumble and others. He's going to talk to us about deal patterns that tidally influence estuaries.
How you guys doing? My name is Austin Williams, graduate student at Oregon State University, and I'm in the Marine Resource Management program. And I'll be talking to you about fine scale diel patterns of tidally influenced communities within shellfish aquaculture habitat. So this work was done in conjunction with the West Coast Aquaculture Collaborative, funded by Sea Grant to advance sustainable aquaculture on the Pacific Northwest. It might echo some of the work you just heard, so hopefully you don't get bored, but it has taken a slightly different approach. My work was focused on habitat use of Pacific oyster aquaculture sites in Tillamook Bay, Oregon. And it's building on previous research and current research that characterizes fish and habitat use fish and nekton occupying shellfish and eelgrass habitat. So I was interested in how community structure changes over the diel cycle in and around aquaculture habitat and how it's influenced by the tide. Specifically, I looked at species composition, abundance, and diversity between habitats. This work was performed by placing some cameras out in several different varieties of habitat within the estuary with different eelgrass densities on both on-bottom and off-bottom aquaculture. And you can see this map here is a map of our sites, and these are all screen grabs from each of the video cameras. And you can see the nice clear water tends to come from these eelgrass beds that are out in this region, where the murkier water is closer into shore, in the on-bottom aquaculture area. So, there's a little screen grab of a nice little staghorn sculpin, and we had both forward and downward facing cameras. The downward facing cameras tend to capture more of those cryptic species like the flatfish, and the forward facing cameras tended to catch more epibenthic species that were kind of living just above the surface. So the video was reviewed by myself, and all the nekton were identified as species, and a second disc was placed in the center of the frame to kind of give a metric for the water clarity. And so I developed this water clarity index that was used kind of across the consortia effort, and we had a lot of 1s and 2s, a couple of 3s and 4s from time to time. The water visibility was definitely the biggest limiting factor of using video to conduct this work. But the total counts were converted to observation per unit effort. It's similar to catch per unit effort, but I figured we're not really catching anything, so I called it an observation. And overall, we collected 1,600 2-minute videos totaling 57 hours of footage, and observed 2,400 individuals across 21 taxa. That's not including 700 videos that were removed due to low water quality. Let's see if this works. So we got some shiner perch, staghorn sculpin, green crab. This was a really busy video. It's like we almost get all the major components of this community in 30 seconds. And we had a lot of footage that was just nothing. And then occasionally we had some nice footage like that. Okay, so I performed a NMDS, which is non-metric multidimensional scaling analysis. And all you really need to know about that is that points closer together are more similar, or points further apart are more different. So you can see these are color-coded, so the blue night data points are kind of tightly, maybe loosely clustered in this region. and the daytime data is out here. And so we can look at how individual species contributed to this variance through a principal component analysis. And basically all you need to know about this is that the magnitude of this line and the direction of it indicate that species contribution to the variance. So the smelt contributed a lot to the nocturnal communities, while the shiner perch contributed kind of equally between the daytime and nighttime communities, where the Dungeness crab, didn't have as big of an impact, but it was mostly focused on the daytime. And because there's such a big difference between the day and the nighttime communities, it makes sense to kind of break them up and look at them independently. So if you look at this little legend here, I color-coded eelgrass to have kind of a green hue, sites without eelgrass are red, and sites with oyster aquaculture are solid. And you can see that habitats with eelgrass are pretty different from those without eelgrass, except for this little guy here, which is actually on or off-bottom aquaculture, kind of indicating that maybe off-bottom aquaculture is giving some kind of structure or habitat functionality that's similar to eelgrass. And this is also where we're seeing an association with shiner perch, which was determined to be a significant association through a Permanova analysis. If we look at the nocturnal trends, it's a little more kind of scattered. There's a lot more variation interweaved with kind of different habitats mixing. In the previous graph, the solid symbols were more close together, and here there's a lot more mixing. So there's less of a difference of an aquaculture effect during night and day, and the species aren't really driving variation, in this model. And this becomes more clear when we look at 95% confidence regions using bootstrap averages. And the biggest difference you're going to see right off the bat is the nocturnal differences there's a lot more overlap, and the diurnal differences between the groups are much more separated. And if we go to the top row here, we'll see the sparse and the dense eelgrass have pretty good clustering, and then the non-vegetated habitat, there's a lot more variability, but they're still distinct, and that distinctness, it degrades a little bit during the nighttime, but it's still there. And then oyster culture type at night, we see good distinction between the aquaculture on bottom and no aquaculture, while off bottom is kind of a mixture between the two. But then at night, all of those communities kind of intermingle and overlap, indicating that the communities that use these habitats are less dependent on them during the daytime. And that becomes even more evident when we just look at presence or absence of aquaculture, regardless of culture type. And we'll see yes aquaculture, no aquaculture, and there's a little bit of overlap at night, but it's a lot more distinct than we see up here. And when we look at species-specific habitat associations, only shiner perch, saddleback gunnel, and staghorn sculpin were significantly correlated with habitats using Wilcoxon rank sum analysis. And shiner perch and saddleback gunnel were associated with eelgrass, and staghorn sculpin were more associated with bare bottom. No differences between species were observed at night as far as their habitat use. And an interesting finding was that abundance was higher on the ebb tide as compared to the flood. And we saw this really significantly in the smelt populations, which would basically come in over the tidal flats as the tide was incoming, and perhaps they use the tidal channels to leave the area as the tide flooded out. And then polychaete worms were another important part of the community that are a prey item for some fish species. And we would see that they would come out of their burrows on the incoming tide, use that habitat, and then burrow back in the mud as the tide left. So it could be just interesting to know how the habitats are used, and when they're used, it just kind of contributes to that story. And then we looked at species richness and diversity, and basically what we found was that species richness and diversity was greatest where we had dense eelgrass and on-bottom aquaculture, and then sparse eelgrass with bottom aquaculture. That's when it was greatest. And then you can see that the no aquaculture with off-bottom kind of was more similar to the sparse eelgrass, but was also similar to the bare bottom habitats. And that basically held constant across, if you look at just the diurnal communities, the nocturnal communities, or if you combine them. The dense bottom eelgrass was always the highest diversity and had the most species richness. So in conclusion, the community structure of diurnal and nocturnal communities does vary, and that was largely driven by the highly abundant species such as smelt and shiner perch. Few species actually exhibited habitat correlations, and these were the shiner perch, saddleback gunnel, and staghorn sculpin. And the greatest abundance of fish was observed on the incoming or the ebbing tide, and shellfish aquaculture may increase species diversity and richness when cultured alongside eelgrass. And that's kind of an important point for aquaculture, I think, is that there's actually a host of ecosystem services that aquaculture can provide to the environment, and the impacts may not always be negative, as a lot of opposition is kind of coming our way these days. So I'd like to acknowledge Brett Dunbald, Nate Lewis, Brooke McIntyre of USDA, Katie and Fiona, who you just heard listening or speak, were actually pretty helpful in helping me design everything, so I'd like to thank them. And then I'd like to thank Sea Grant, USDA, Sexton, based out of Salem, Oregon, for the contributions of helping me design the video cameras, and then Pacific Shellfish Institute. Questions?
Time for one question. How much did you?
Just curious, for the study set up, how does the start during the summer? I thought it finished from June, so the low tide was during the day, and the higher tide was at night. Do you think that had an influence on species?
Yeah, I didn't separate that out, but within the literature, that there's definitely a neap ebb effect with species composition, and I just haven't got that far into the analysis yet. Thank you.
And we'll bring all the speakers back up at the end. I know I've got more questions for each of them, so I hope that you guys will too. So please join me in welcoming our next speakers.